All right. So the main thing I wanted to get at today was, I guess my title here, coupled coils and transformers. So coupled coils basically means that I got coils that are one coil is coupled to the other one, meaning it's throwing flux into another coil. And I have a specific reason why I'm not using just the word transformer, but coupled coils. Okay. And the reason for that, I'll jump ahead here for a second, right? Is I showed a picture like this before. This guy is what I call an induction motor. We're going to learn about these after spring break. Induction motor is what you use for most motor applications. Three-phase motor. And a cross section of it would look like what I've shown right here. All right. And we're going to look at that picture. When I say a cross section of it, basically what I'm saying is if I took a slice basically right through the middle of that motor, this is what that slice would look like. This is idealized. If we actually look at it, and we'll look at one on the inside, but when you look at it, what I'm trying to show here is AS and AS prime are basically, so I showed you that coil last time that I brought in last week. Like AS and AS prime are two sides of that coil. Okay. If I look at this coil, AS, BS, and CS, those guys are all throwing flux through each other, but this thing is not a transformer, right? So the coils are coupled to each other, magnetically coupled. And there's also this, so S here means stator, basically a stationary piece, and R means rotor or rotating piece. We'll talk about what those terms mean later, but this is a classic situation. I got 6 coils that are all kind of pushing mutual flux through each other. All right. That's a term I use for the first time, mutual flux. Some of you guys I know what that means, but if I use the term mutual flux, what does that mean? Any idea? If I've got 2 coils, let's say I got one coil here and another coil beneath it. So I think 2 weeks ago, I brought in 2 coils. I put one on top of the other, right? And what I did was I hooked up a function generator to one of them. What's going to happen at the other coil? There's going to be a voltage. All right. Now, what causes that voltage to appear?
The current in one.
Well, yeah, the current in this one creates a flux, right? And where's that flux going to go? Well, that flux is going to go around like this. So there's basically Faraday's law. So I have a flux from the bottom coil going through the top coil that induces a voltage on the top coil. This flux here I sometimes call a mutual flux because it goes through both of them. Yeah. All right. It passes through both. All right. Now, one of the things I did a video to kind of capture this, but if I just put one coil on top of the other, if those 2 coils have the same number of turns, and I put 1 volt right here, what's the voltage on the top coil? If I just put them right on top of each other, it's going to be less than 1 volt. To make them, now you guys know if I have a transformer, if they're the same number of turns, you probably already know this, right? If they're the same number of turns, what's the voltage supposed to be if I put 1 volt? 1 volt, right? 1 volt, 1 volt. In reality, what I have to do is if I just put them right on top of each other, it's not going to work. I got to make sure that flux really gets through the other coil. To do that, that's why I need a core. Core makes sure that the flux goes exactly where I want it to, just straight through the center of the coil.
And the core is the thing that would go inside.
The core, yeah, the core is this guy, right? Without that core, the flux isn't going to direct the way I want it to. It's going to go out and around, and not all of it is going to go through the other coil. All right. And you can see that. That's what I was trying to do the other day. And I figured out why I didn't. I had 2 cores that were different materials. So it wasn't quite, they weren't fitting together quite right. If I take those 2 halves of a coil like this, or core, and I stick them together, then you see if these guys have the same number of turns, the voltages are the same. All right. Now I also said I put 1 volt on here, right? Can I just put 1 volt DC on one side? If I put a battery on V1, would I get anything on V2? Yeah, it would be a very low resistance that's on there, that's for sure. But if I put a battery here, so if I put, basically if I wanted a 1.5 volt battery, I'd get a AA battery. If I put a AA battery right there, there would be no voltage on the other side. Why is that? The magnetic field would be constant. What's Faraday's law say? Changing magnetic field to induce a voltage. All right. So one reason why we use transformers is that actually can separate the DC voltages of two circuits. So one side could be grounded and the other side could be at 10 kilovolts. All right. So there's good reason for that. In fact, anytime I'm like hooking up a PV inverter or something to the grid, usually I do it through a transformer. Okay. No, it's not high passing. And that, I mean, I guess let's stay away from words like that for now. All right. It's basically, it's ensuring that I have what I'll call DC separation. All right. Sometimes that's called galvanic isolation. Some of you guys may have heard that term. All right. Anyway, there are two principles I said. I'm going to keep coming back to these that I need in any of these energy conversion problems, right? A wire in a magnetic field can produce a force. We haven't really talked about that one yet, right? But you guys know it. F equals I cross B. You saw that in physics, right? And you probably saw that in fields too. The one I'm dealing with today is this one. A wire placed in a changing magnetic field can serve as a generator, right? If I have a transformer is two coils coupled together. If I stick a source onto one side of this guy, like that, over here, V2 is a generator. All right. Basically, he acts like a voltage source as far as anything connected here is concerned. He looks like a voltage source. All right. It's the basic idea of what a transformer does. All right. So let me just a couple of basic notes on transformers. So this is a pretty typical transformer that you see on the left, like a building transformer. So a couple of things. That's what it looks like from the outside. On the inside, it's a magnetic core, and it's done in those pressed iron sheets like I talked about last time, right? And why did I say there's those iron sheets in it? Talked about that at the very end. What do the fact that there's iron sheets do inside this thing? It helped with the power loss, right? So if I have flux going through a magnetic core, what's that flux do? What do we say about steel and iron? They're conductive, right? So so the flux going through that core induces currents in the core itself. Well, Faraday cage basically is to block fields. It's for interference protection, but it's a similar kind of concept, right? So I said, you induce currents inside the core. You also had what? You also said if I put a voltage on the coils, and that creates a flux inside of the core, we basically said we had those little magnetic atoms, basically, dipoles moving around inside of that thing. So if I touch that core, it's hot. All right. Now you don't touch the core itself. What I have there is an outer shell, and notice along the top here, I've got a vent, all right, for air to sort of pass into it. All right. The key thing with the transformers is going to get hot, right? The core is getting hot. Okay. It's also the case that the windings are going to get hot, right? Because why are the windings going to get hot? I say the windings, basically, the coil itself is going to get hot. Why is the coil going to get the current through it? Yeah, there's I squared R basically inside that thing that causes heat. If you did a thermal image of that, you would see it getting warm. Okay. All right, and this is a typical nameplate here. So I see a couple of things here on the nameplate. Transformers, they never tell you N1 is this and N2 is that. You don't know what the number of turns is, right? If I'm looking at this case, a nice good old square D transformer, right? It's not going to say how many turns are on the primary and how many turns are on the secondary. What it's going to say is the high voltage side and the low voltage side. All right. So in this case, the high voltage side is 480. The low voltage side is 208/120. All right. So how's 208 and 120? How do I get from 120 to 208? multiplied by the square root of 3, right? One's a line-to-line voltage, one's a line-to-neutral voltage. Okay. This is specifically, if I'm going into the power grid, so this is, there's a couple of these throughout Epic. Epic gets a 480 volt service. There's going to be, for all of these outlets down here, there's a 120, right? So somehow the voltage had to be stepped down. So it gives me a high voltage and a low voltage. The other thing that matters is here, it has a kVA rating. And it's hard to see that there, but it's 150 kVA. So 150 kVA. So in our little power triangle here, who's that? Who's 100? What's units is kVA? It's apparent power, right? This basically means that that's the maximum S, magnitude of S. All right. S is a vector. Magnitude of S is a number. All right. And that's a pretty typical way to rate stuff, because what it tells me directly is, if I'm putting 480 volts, 150 kVA, I can get direct to the maximum current that I can ever pass through this thing. All right. Where does that number come from? Basically, the maximum amount of current I can pass through here. If I pass more current than whatever this rating tells me, transformers can get too hot. All right. It's a thermal rating that controls the rating of the device. All right. So I think in the homework there on number 5, I think I told you it was a 50 kVA transformer, right? From that, I think you get one of the numbers. I think you get the current number. Okay. All right. One thing you notice here, the high voltage side, the low voltage side, it tells me the amps. You should probably know this but the side with that more voltage always has less amps, right? Ideally, this guy is our first kind of energy conversion device that I'm dealing with. If I put a voltage on one side, there's going to be a voltage on the other side that's induced. What's true about the power in this thing? Yeah, whatever power I put in the primary is going to equal whatever power it comes out on the other side, minus the losses. All right, and the losses come in the form of the core heating and the winding heating. Okay. All right, so basic sort of stuff that we would see sort of in the real world. All right, so a couple of things, but we get into these coupled coils. I want to make a couple of notes about directions, because one thing it gets confusing. The whole thing, Lenz's law is to me a goofy physics thing. I don't like thinking about it. It just confuses the crap out of me. So I have a way that I like to think about this, which I think is simple. All right, by convention, we always show that picture there. So V of t is across the coils, and I show a current going into the plus terminal. Right? So that's our basic passive sign convention stuff from circuits 1. All right. That's the way we like to do this. So when I look at this, if I had this, I shouldn't have put the arrow on there, I guess, but how would I figure out? I showed the flux going up through the center of this thing. How do I know it's going up through the center? Right-hand rule, right? So if I put my thumb in the direction of the current going in, my fingers are going to curl up. So the flux is going to go through the center of it. Okay. So a flux that if I have a coil like this with I of t defined like this, I would call this a term I'm going to use. This is what I'm going to call self-flux. Meaning that's a flux that this current itself created in its own coil. Okay. So what if I have a mutual flux? Meaning there's some other coil. So let's say this material was, continued on like this, and there was another winding over here, right? Right, and that other winding was producing a flux passing through this guy, right? I called this guy phi sub m, meaning it's a mutual flux. It's coming from somewhere else. Okay. Lenz's law basically tells me this. If I have that flux going through that coil, and it's coming up like it is right here, that's going to cause a current to flow out of this thing. All right. And the voltage would have the plus and minus directions like I have right there. All right. Now, first of all, the way I've shown this guy right here, there's an open circuit on it. So is there any current that's flowing? No. All right. But if I hooked the load up to it, that's what would happen. All right. Now, let's say I want to relate this guy. I want to relate the flux phi m to that voltage V of t. How would I do it? How would I relate V of t to phi sub m? So help me out. How do I get V of t related to phi sub m? There's a flux going through there. How does a flux produce a voltage? What's the law? If I've drawn it with the signs that I have right here, it's D. So just a reminder, the flux linking the entire coil, we say is lambda 1 equals N1 phi m, like that. All right. So phi m is what I call this flux. The flux linking the entire coil, right? Phi m goes through each one of the coils. N1 times phi m is the flux linking the whole thing. Okay. If I write it the way I did right here, there's no minus sign. It's d lambda 1 by dt like that. Okay. So if I write that, if I take the derivative of that, it becomes n times d phi m. Get rid of that picture by dt. So the way I'm going to think about this is that this guy, here's V of t. I have this little voltage source here, n times d phi m by dt. This guy's like a dependent source. All right. Dependent because somehow it depends on a flux that's coming from some other place. All right. And we're trying to make sense of that here in a second, but that's basically what I have here. And what this is saying is if phi m is going up through this guy, as I've shown, then the current will flow out of the coil and the voltage will have the polarity shown right there. Okay. Now, the way that I always think about this is, so whenever the self flux and the mutual flux are in the same direction, then they have the same sign. Okay. So in other words, when I'm looking at this guy right here, if I had a current I going in right here and the flux phi m going through here, which direction would the self flux be? In other words, what direction would the flux coming from this current, which direction would that be? Be up. Right? So so this is phi m, this would be phi self. If I said, what's the total flux going through this thing? It would be phi equal to phi self plus phi m. It just adds up. All right. Whenever the current into the coil produces flux in the same direction as phi m, right? That to me is the way that I typically sort of think through this stuff. And I just kind of forget the whole Lenz's law thing. All right. And we're going to look at some examples of how we use that here. Okay. All right. Okay. All right. Key thing, and this is what we do anytime we start looking at like a device like a transformer, a motor, whatever. Basically what I'm trying to do is I don't, from the perspective of a user of the device, I don't really care about the magnetics. I care about what it does in an electrical circuit. So I want an electrical circuit model for these things, for a system with these coupled coils. To build an electric circuit model, I basically have two steps. I draw out from the picture of the magnetic thing, right? I draw out the magnetic circuit model, and then I use Faraday's law to go from the magnetic circuit to the electric circuit. What's always going to be in the electric circuit model? So the magnetic circuit model has reluctances and stuff, right? Once I go from the magnetic circuit model to the electric circuit model, what components are going to be in the electrical circuit model of a magnetic device? It's going to have basically inductances because it's got windings on it. So it's got L's, and because there's losses, it also has resistances, right? So L's are basically the primary thing that comes out of that electrical circuit. model. Okay. All right, so let's start. What happened to my? All of my hang on. Crap. Hang on for a second.